Okay, welcome to lecture 3. So today we're going to cover curvilinear motion, some more curvilinear motion. On Tuesday we talked about Cartesian coordinates, which was just x, y, z coordinates. Imagine we just fix our coordinate system to the room and we track the motion of an object through that room. That's probably the most familiar, most comfortable, and it has a pretty wide range of applications that it works for quite well. And then we use projectile motion, which is quite convenient for that type of motion or analysis. So today we're going to look at two other coordinate systems. First is normal and tangential coordinates, and then next is cylindrical coordinates. So what are those? First, let's just start off with a question, see if we've been reading along at all. So the normal component of acceleration, when we talk about normal and tangential components of acceleration and velocity, the normal component of acceleration represents what? The time rate of change in the magnitude of the velocity, the time rate of change in the direction of the velocity, the magnitude of the velocity squared, or the direction of the total acceleration. And we've got B, little b, big B. Ooh, a C in there, good. Yeah, so the correct answer here is B. Fix my pencil. B is the correct answer. C is almost the correct answer, except if we had the magnitude of the velocity squared divided by the radius of curvature, then that would be how you would calculate that normal component of acceleration, but it's not quite. So the correct answer here is B. So what are normal and tangential components? So sometimes when a particle is moving along a curved path, it's more convenient to describe the motion in different coordinate systems other than Cartesian. And if you know the path of the motion, oftentimes normal and tangential components are more convenient to use. So we can just say often more convenient if the path of motion is known. So we would have two components, normal, which means perpendicular to the path, and we use the variable n, so our units and velocity, acceleration, things like that will have subscript n, and then we also have tangential. And that'll have subscript t. So in the nt coordinates, or normal tangential coordinates, the origin now is actually located on the particle as it moves along the path. So the origin is located on the particle as it moves. So we can see that here. We have our n and our t. These coordinates are going to move along the path, and then our un and our ut are the unit vectors that define the coordinate system, and that'll be the directions that are, those would be the directions of our normal and tangential components of our velocity and acceleration. So let's do, for example, if after some time, maybe our particle moves over here, our tangential component, ut would be here, and this would be a vector. And at this point, it looks like the curvature changes and we start curving downwards again. That normal component of our coordinate system is always going to point towards the inside of the curvature. It's always going to point towards the center of the radius of curvature. So in this case, our normal component would be over here. And maybe as another side note, the magnitudes of these unit vectors, because they are unit vectors, are always equal to 1. So the t-axis is always tangent to the path. Seems kind of obvious. The t-axis is always tangent to the path. And at the instant that is considered, the positive direction is always in the direction of the particle's motion. So t-axis is always tangent to the path and in the direction of motion. And then lastly, the n-axis, like we just covered, is perpendicular or normal to the t-axis or the path. And its positive direction is always towards the center of curvature of the curve. The n-axis is always perpendicular to the t-axis. Or we could say path. And always points, the positive direction is always towards the center of curvature of the curve. So, and let's say the positive direction is always toward the center of curvature. So here in the diagram, we have our origin O dot. This is our center of curvature. So we defined these units, where they are in space. So we know the positive directions of n and t are defined by those unit vectors. So let's write positive directions defined by our normal and tangent unit vectors. Center of curvature is always O, and the radius of curvature we will give the value of rho, the variable rho. So rho is Greek symbol and it is the radius curvature. So this radius of curvature isn't constant, but for any instant in time, we consider the radius of curvature at that specific point on the curve constant. It is changing, and it depends on the actual path itself. So that's how we define position. Position is not with respect to any fixed point in space, it's with respect to where the particle is. So the particle is constantly moving. So if we think of normal and tangential components, think of you're sitting in your car and you know the speed you're going at and how much you're turning, essentially. And from that, you can calculate all of your other components of your velocity acceleration. So think of speed and direction is the two pieces of information you have. So when we talk about velocity, our velocity vector, same thing with any velocity, any coordinate system we have. The velocity vector is always tangent to the path. So our velocity, properties of velocity haven't changed. So velocity is still always tangent to path. So we can write the velocity as the speed times the direction of that path. So if we write our velocity vector can just be equal to our speed. Looks like a U, let's try and make it look a V. So our speed V is not a vector, it's a scalar quantity, and that's multiplied by our unit vector that represents the tangent direction. So we would have UT here and UN here. And this is convenient if we know a function of the path, because if our path function is known, and path might be some function s as a function of time, we can calculate our speed as the derivative ds dt. So the rate of change of the motion along our path over time. And this would be our speed. And this vector here is our velocity. So the speed is essentially the magnitude of the velocity, and then our unit vector ut defines the direction of that velocity. So v is our magnitude of velocity, and u subscript t is the direction of velocity. Good, so that's velocity. Velocity is usually pretty straightforward. It's not too confusing, but then once we get to acceleration, that's when things tend to get a little more confusing. So we know the definition of acceleration is the time rate of change of velocity. So when we define that with rectangular coordinates, it was just the time rate of change of our velocity vector, which was the second time derivative of our position vector. So in this case, we don't really have a position vector. Our position is just defined by the unit vector directions ut and un, and we have some path function s. So how do we actually calculate acceleration in this case? The definition hasn't changed. Acceleration is still the time rate of change of velocity. So if we write down our acceleration vector is equal to the time derivative dv dt. And if we use our definition of velocity from just before, the previous slide, we can write it as a time derivative ddt of our speed times that tangent unit vector. And if we do product rule, this ends up being v dot times ut plus v times u dot, or ut dot. So if we look at each of these terms, our v dot represents the change in the magnitude of the velocity. So change in speed. So how fast is the speedometer in the car changing? And then u dot t represents the rate of change of the direction. So this is the rate change of direction. So how do we actually calculate rate of change of direction? Well, if we look at what's actually happening here, the rate of change of direction is related to this angle d theta. That is basically how much we're rotating around the center of curvature. So over a very infinitely small amount of time, that ut vector is just going to be rotating, and that rotation is proportional to d theta. And then if we relate that back to the path, we can do some manipulation, which is in the textbook. You can read it if you want. We don't really have to go through it. But what we have is our final equation for acceleration is going to be equal to our change in speed times our tangent unit vector plus our speed squared divided by our radius of curvature, rho, times our normal unit vector. And then we break these up and we call these our tangent component of acceleration and our normal component of acceleration. So AT and AN are just scalar values. They're just numbers. And when they're included with our unit vectors UT and UN, that gives us our acceleration vector A. So this is the equation for our acceleration. So what we can write is the total acceleration just equal to tangent component times UT plus the normal component times UN. So like it suggests, AT is tangent to the curve and is either increasing or decreasing the velocity. So AT is always tangent to the path. And it's in the direction of increasing or decreasing velocity. So if AT is positive, we're accelerating. If AT is negative, we're decelerating. So if AT is greater than 0, we're accelerating. And if AT is less than 0, we're decelerating. We're slowing down. The normal component, AN, is always pointing towards the center of curvature. It's pointing in the same direction as UN. And we call this the centripetal component or the normal component. And it acts towards the center of curvature. So AN is normal or centripetal. Acceleration. And it is always pointing toward the center of curvature. And then lastly, we can write the magnitude of our acceleration, just like we write the magnitude of any vector. It's just equal to the square root of the sum of the squares of its components. AN squared plus AT squared. And this would give us our total acceleration, or the magnitude of our acceleration. So let's look at some special cases. What is the special case where we have an infinite radius of curvature? What type of motion when we have, what type of motion do we have when we have an infinite radius of curvature?
Probably only tangential, just because it would go to 0 for the
right. Exactly. Yeah, so our AN was equal to our speed squared divided by our radius of curvature. So if this denominator was infinite, then this would go to 0. So we would only have tangential acceleration, and we would just have motion along a straight line. What about the case where we have particle moving along a curve at a constant speed?
There's no acceleration in the tangent, so it would only be the normal acceleration.
Right, so our acceleration would be purely normal acceleration. So in this case, our AT would equal V dot would equal 0. Our AN would equal just our velocity squared divided by rho. And just so we can remember, this is our O prime. This distance here is that radius of curvature, rho. So distance towards the center of the radius of the curvature. So if we think of part 2, if you've ever familiar with driving, one of the things they say when you're driving to have the maximum grip around a corner is to not be accelerating. If you're accelerating, you're increasing that total acceleration vector, and that's putting more strain on your tires for grip. And friction can only provide so much force, and if you try to accelerate through a corner, you might slide off the corner. So the best way to get through a corner when you're driving, we can see sort of quasi proof just based on this, is to have 0 change in your tangential velocity, or have your tangential acceleration be 0 and you're just holding a constant velocity through a corner. Good, so let's write last thing here. Only normal acceleration. So what about, let's say this time the tangential component of acceleration is constant. So what can we do if our tangential acceleration is constant? Are there some equations we've derived before or come up with before that we could apply here? So if we have constant acceleration and we have linear motion, we came up with some equations of motion that we used for projectile motion in the vertical direction, or just motion of a particle along a straight line path. So in this case, we have a curved path, but because we're describing the motion and the axis is moving with the particle, we can represent the position along the path the same way we would with a straight line path, because of how we've defined the coordinates. So we can use those constant acceleration equations of motion that we came up with. So in this case, if our path is S, if path is defined by S at t, then we can say our equations of motion from before, S is equal to S0 plus our initial velocity times time plus 1/2 our tangent acceleration, which is now constant, times time squared. So we'll call this constant acceleration. And then our next equation, velocity is equal to our initial velocity plus that constant acceleration term times time. And then our third equation, our velocity squared is equal to our initial velocity squared plus 2 times our constant acceleration times our current position minus our initial position. So we have our 3 equations of motion. So here S0 and V0 are the initial position and velocity when t is equal to 0. So s is 0 and v0 are initial conditions, we'll say. And there when t is equal to 0. So we have equations of motion we can use if we know we have constant acceleration along the path. Now, our normal component of acceleration would still have to be dictated by v squared over rho. But our tangential motion, or motion along the path, we can describe using these equations. The last useful equation, I guess, would be if we know the actual shape of that particle path, then we can calculate the radius of curvature at any point in the path so that we can calculate that normal component of our acceleration, because we need to actually find the radius of curvature. And if we're not just moving around a circular path where it's easy to calculate the radius of curvature, we can use this function to help us out. So if particle moves along a path, and that path is defined as y is some function of x, so in 2D, then we can write the radius of curvature rho, don't be intimidated by this, is equal to 1 plus the derivative dy dx squared to the power of 3 over 2 divided by the magnitude of the second derivative d squared y dx squared. Not the magnitude, the absolute value. So if we know a function y as a function of x as our path, maybe another way to write this that might be less frightening would be 1 plus y prime squared to the power of 3 over 2. All divided by the absolute value of y double prime. So that term in the denominator is always going to be positive. Fix my bracket here. So we find the first derivative of the path y with respect to x, find the second derivative, and we put those expressions into this equation, and we get a function for the radius of curvature at anywhere along the path. And then we can substitute in our values of y and x along that point in the path and calculate the radius of curvature at any specific point. So that covers everything for 2D motion. We're not going to go too much into 3D motion because a lot of 3D motion using n and t coordinates, you can just resolve this back into 2 dimensions by thinking of at any instant in time, there is something called an oscillating plane, and the particle's motion is within that oscillating plane. And that oscillating plane might move through space, but at any moment in time, we can resolve it back down to 2 dimensions. So in 3D, the particle moves along a space curve. We'll call it. And we can define the n and t axis the same as before. So n, t axis defined same as before. where we have n pointing towards the center of curvature and our t is pointing along the direction of the path. And now all we're going to define is some extra term, and that is going to be UB. So UB, or the B axis, which we define with the unit vector UB, defines the unit normal for the what we call the oscillating plane. So if we use our definitions of vectors and vector products, we can actually calculate that UB if we know UT and UN. And UB, we can just say, is equal to the cross product of UT cross UN. And just so we know this isn't times, this is our cross product. So in that oscillating plane, whatever direction that happens to be at any instant in time, there is no motion in or out of that plane. All the motion is contained within that plane at that instant in time. So all of our motion is UT and UN. So likewise, we can rearrange this equation if we know at some point in time where the oscillating plane is, and we can describe that vector UB. And we might also know the tangential component to the path. Then we can calculate UN, or vice versa. If we know UB and UN, we can calculate UT, and then we have our 3 unit directions describing our motion. And we know that the motion in UB is always going to be 0. There's no velocity component in that outside of the oscillating plane. For most problems in this course, we're just going to stick to 2 dimensions, but later on, when you get to Dynamics 2, you will probably be dealing with some 3-dimensional motion. So this is just a bit of a maybe teaser, I guess.